Okay, so let's get started today. So, hi guys, I'm Nick. I'm an application engineer on the Markforged's AE team, and we wanted to take some time today to discuss, when's a good time to use 3D printing, metal 3D printing specifically, and when you're deciding to use it as a technology, what are some strategies and design techniques and sort of considerations to think about in order to produce a really successful application. So, with that. Really excited to talk to you guys about metal today, and let's get started. One second. So just a little background on myself. I'm a mechanical engineer. I've been working at Markforged for about 4.5 years now, and I spend a lot of my time working with manufacturers specifically to develop their design skills and their team's design skills, and to focus on how to adequately or appropriately use 3D printing to make a big impact in their business. And not just 3D printing things for the sake of it, but specifically designing parts for the process and to take advantage of it. And what we found a lot is that really incorporating design for manufacture at every step of the way is highly important to actually making successful use of 3D printing. And so you really need to consider all aspects of the process and what you're trying to achieve in order to make those use cases successful. So with Markforged, for our metal technology, it's called atomic diffusion additive manufacturing, or ADAM. And we print those parts on our printer known as a Metal X. And so just a couple things to think about is that with the Metal X, it's a safe, cost-effective way of actually 3D printing metal. From a process standpoint, and we'll talk about this in a second, it's printing with a filament extrusion-based technology. And our materials are based on the MIM process, or metal injection molding. And so what that looks like as a process, to get us started, is very similar to metal injection molding with a few specific changes. And so metal injection molding is roughly a 30 to 50-year-old proven technology. It is a way of generally making really complex, repeatable, and in the case of metal injection molding, generally small parts. And we've actually sort of improved upon that with our ADAM technology. But the way it works is you're going to design a part to your nominal dimensions in CAD. You'll then get that into our Markforged's Eiger slicing software, and you'll send that off to a Metal X printer and you print it. And that's producing a green part. And that we call it a green part because it's composed of a metal powder and two different types of binders. One's a plastic and one's a wax. It's all sort of mixed together into a filament, and you'll print that very similar if you've ever been familiar with sort of fused filament fabrication or FFF print technologies, very similar to that technology. So you print that part into a green part, as you see here. You'll notice that green part looks a little bigger than our design part, and that's because we actually scale it up to account for future shrinkage later on in the process. We then take that green part and we put it through a washing process to debind it, and that's going to produce a brown part. So that wash process removes basically the wax component of that binder. And then finally we put that into a sintering oven. We'll burn the plastic component of that binder out of the part, and then we'll also sinter that part, and it actually, as it sinters, it actually shrinks down back to your nominal part size. This is our ADAM process. It's important to note where we start or what the process we're using so that we can then design around the capabilities of the process. And just to give you a little bit more insight into what this looks like from a more microscopic view. So if we're looking at the various constituent parts of a ADAM part, you're going to have a metal powder, you're going to have a wax, and you have a polymer, as we talked about. So at a microscopic view, maybe a small section of your part might look something like this after printing. So when you have a green part, so it's going to be composed of all three of those materials. When you put the part through our debinding process, our wash one, it's going to remove that wax. So you effectively have a part that looks something like this. And the part has not changed in dimensions during this washing process, but it's removed some of that wax. So you now have a part that's semi-porous. And that's actually important for later on in the process. So you've basically removed all of the wax binder. And so the part is composed at this point of the metal powder, and it's held together by that polymer or that plastic binder. During sintering, early on in the sintering process, you'll start burning out that polymer binder, and that burns out through those porosities that you generated by washing it and washing away that wax. And that's really important to preserving, good dimensional accuracy. As sintering progresses, the metal powder will start to link and start to weld together a little bit, sort of form bonds like you see here. And then kind of the atomic diffusion part of the atom process happens during the sintering, where you're never melting these metals. It's about 85% of the melt temperature of the underlying metal. But they diffuse, the particles diffuse together, and your part shrinks down and forms a solid part, as you see right here, composed of those, or formally composed of those metal, small metal powders. And so after that extended and gentle sintering process, it shrinks back down. It's because it's based on this MIM technology, it's a highly repeatable process. MIM's used for anything from the hinges in your eyeglass frames to the lightning connector in your iPhone. It's used to make really highly repeatable parts, and the process is very consistent. And so also when we talk about that part scaling, just to give you an idea of this, you're designing to your nominal dimensions, and we'll talk about some tolerancing and things to think about later. We scale it up in our Eiger software to about 20% larger, and then it sinters back down to that as designed size. But what you should consider for all of this is that we're printing near net shape parts, which means that if you have a part that doesn't need a machined tolerance, for instance, if you need something that's going to be a bearing press fit or a critical machine surface like that, you're going to still want to finish those. All other surfaces are going to be kind of near net shape. It's something like, plus or minus 5 thou per inch kind of tolerance. So in many cases, you don't need to finish all faces of a part, but you will need to consider that sort of in your design as that you will need to potentially do some finishing operations for critical dimensions. So now that we know what the process looks like, let's talk about some steps to think about when you're considering whether metal 3D printing is a good choice, or while you're designing for metal 3D printing. So the first thing you're actually going to want to do is unrelated to design entirely, and that's you're going to want to make sure that your part and the sort of volume requirements and the economic requirements of your part match up well with 3D printing's capabilities. Once you got that, and once you've found a part that meets that, you're also going to want to make sure that your part has suitable geometries to the process. You wouldn't, injection mold a part that was intended for sheet metal forming, and similarly, you want to make sure that you have a part that's going to be suitable for the metal 3D printing process. Assuming you pass those first two filters, we'll then show you how to modify your design a bit to take advantage of the capabilities of the atom process. In many cases, atom and the metal 3D printing process are pretty similar to, or can produce pretty similar parts to either cast or machined parts, but there's still ways that you can modify your designs to take even further advantage of the capabilities of the process. And then finally, you're also going to want to plan ahead for finishing operations. So we talked about producing near net shape parts and ones which you may need to machine or grind or tumble, whatever it is after the sintering process. You're going to want to plan ahead to make sure you're leaving enough material to take those operations into account. Let's dive into it. So first, we want to make sure, this is something that our application engineering team deals with a lot. We oftentimes talk to customers that want to print a certain part, and we take a step back. We want to look at, what are the volume requirements, what are the economic requirements of those parts. So this is a pretty common, you've probably seen this a graph or something similar to this graph before. This is a graph of the sort of economies of scale of traditional processes like machining and casting. And generally what you see is that for low volumes, they have a pretty high cost per part because you're trying to get things set up, whether that's your casting tooling or whether it's you're getting your machining operations set up and getting ready to run. But as you start to increase your production volumes, the cost per part kind of amortizes out those sort of fixed costs, and you get a pretty economically attractive cost per part. And so that's great for a lot of these traditional processes. With 3D printing, specifically with the Metal X, you have a much more flat cost structure per part. which is really nice in the low volume sections, but definitely, obviously, it's a certain point becomes more expensive than a traditional process. So you want to make sure that, you kind of take this into account. And where we generally suggest, filtering out parts for is things that are produced in production volumes smaller than this sort of break-even point where, it's ends up being cheaper on a per part cost to use a traditional process. So really where we see the biggest impact on a business or on an engineering project is sort of in this region to the left of that break-even point. And these are the areas where it's going to generally be much cheaper to print a part at that volume. And you want to make sure that, you're sort of print. Generally, we see is that it makes the most economical sense to print in those ones to hundreds parts range. Generally, we see sometime around 500, 1,000, something like that range, where it starts to become more economical to use a traditional manufacturing process for those parts. There's obviously, this is a generalization. There's certainly there's always going to be exceptions to that, but that's a general rule of thumb is like when you start looking at it, you probably don't want to be metal 3D printing a part that you make in 10,000s, 20,000s, et cetera, especially not in millions. But for those a little bit lower volume parts, oftentimes tooling comes into this really easily. That's in those ones to hundreds and, maybe up to like 500, 1,000 range. That's probably a good starting point. So one of the nice things about Markforged's software is this actually it's really easy for you to actually see, exactly what the economics of a part you're going to be printing will come out looking like. So you can actually see right here in the left-hand side, as soon as you sliced a part, it'll actually give you, our software will give you all of those metrics about your part. And you can kind of make that economic decision from there. So assuming that you've chosen a part that makes sense economically, you next want to kind of look at it and see whether the geometry that you're trying to print makes a lot of sense. And something we see a lot of applications which are really better off produced in other areas. So things that are really not so suited for a metal 3D printing process tend to be things like off-the-shelf parts that you can simply buy. And that kind of includes hardware like screws, washers and bolts, things that are, if there's a established manufacturing process that is highly optimized to produce something at low cost, generally it's not a good idea to actually print those parts. The other ones that we see being not really the best for the process tend to be sheet metal parts and high aspect ratio parts, things that are maybe particularly thin, like sheet metal parts, but also occupy a large cross-sectional area. And also, especially with sheet metal, there's oftentimes you're looking for specific grain structures in that sheet metal, or you're looking to produce parts which the grain structure of your metal follows the geometry of your part. And that's not really something that 3D printing can readily replicate. So those are some of those kind of geometries where it's really not the best call. That being said, especially with sheet metal, it may be, if you need a custom tool, it may be more useful to print the actual tool and then still produce those sheet metal parts with that process. So it's something to think about is do I actually want to print the part, or might it make more sense to print the tool that makes that part? And that kind of goes back to those economic, how many of those parts you're trying to make as well. But on the range of what is well suited for, metal 3D printing, the atom process, typically think about things that are a little bit more meatier of parts, or have a little bit more monolithic, solid bodies. So things like sand and investment castings, especially as they get more complex, can be really good options to 3D print. Parts that you're normally machining out of bar stock or flat stock might be a good point to look at. Generally, a lot of times you're taking away or removing a lot of material anyway, and so with 3D printing, you're gonna basically be adding material only where you need it. And also potentially die-cast parts in some cases. But those kind of, even if the part wasn't specifically designed for one of those processes, and you're designing something from the ground up for 3D printing, as we're going to talk about in a second, it's still sort of your best bets, or your best geometries tend to be something that at least mirrors or is similar to some of these traditional processes, where it's going to be a little bit more of a solid part. And kind of speaking of a part that was sort of redesigned from the ground up for 3D printing, this is actually a example from Stanley Black & Decker, one of our customers, who designed this housing for one of their housing for basically the actuator switch on one of their hydraulic tools. And so they took, you can kind of see the cat on the right-hand side of this. They basically took a component or a housing component that was produced of 4 parts, and they reduced it down by designing specifically for 3D printing down to a single part. And it's, you can kind of see that it's relatively monolithic and kind of in the range of a part that otherwise would be cast or machined. Okay, so okay, let's assume that you've now gotten through those first 2 filters and you found a part that makes sense from a volume perspective, and you have a good geometry or a good starting point geometry. You're also going to want to think about how you might adapt your design for the actual atom process. And you really want to specifically think about designing for the various steps in that atom process as well. And so that's, we have effectively 3 different steps that you want to think about, which is, designing for the printing, the wash, and the sintering side of things. So on the printing standpoint, one of the biggest things to think about is, it's a similar level of design as maybe design for other filament-based, extrusion-based 3D printing. So I'm just going to walk you through a couple slides to it's a little bit of a time lapse of a part printing to kind of put you in the mindset of things you want to be designing for. And actually, this is going to answer a question that we got about our supports needed for, printing and sintering. So the answer for that is yes, and we'll see this in a second. So this is a part that's been printing, and you can kind of see as this time lapse elapses that you're building up the part layer by layer, and adding more material, sort of layer by layer, and building it up. And so a couple things to think about that are important here is that parts are going to build from the print bed up. So you're not building parts in sort of empty space. You're always building them upon a solid foundation. And so to kind of go along with this, you need to always make sure that everything has a solid base to print on, whether it's a part or whether it's supports. So if you were to print over midair, that material would just sag or droop, and so we can't do that. So you do need to have supports anytime that you have an overhang that's greater than 45 degrees from the vertical. And to answer one of the questions we got, you do need supports for both printing and sintering. And that's in order to keep the part nice and dimensional accurate, as well as to support those overhangs when the part gets up to an elevated temperature. And what those look like is there's a couple different components of the metal axe and its supports. So all parts are going to be printed on a raft. And that helps you keep really good dimensional accuracy during the sintering process, actually. It allows everything to shrink really nice and uniformly. As far as the actual support structures, you're going to have this sort of setter structure in the middle of the supports. That's printed in the same material, so it's going to be in the same metal material. In this case, we're printing in 17.4 pH stainless. You want that to be printed out the same material so that it's for shrinkage compensation purposes. So as everything is starting to shrink down during that sintering process, you want everything to shrink really nice and uniformly and gently. And so if you had materials that shrank at different rates, this would become sort of a problem, and you'd be running into more issues. So what we do is we print this setter structure that kind of holds everything into place in the same material while it's sintering. Now, the other thing, though, is you don't want those support structures to actually bond to the part. You want to be able to take them out. And so, or at least you don't want them to bond permanently to the part. So what we do is we also print a layer of ceramic material between the setter structure and the part. And it allows the part to weakly bond to the supports so that everything stays together, and then you avoid any sort of dimensional change or dimensional inaccuracy during sintering. But it allows it to sort of tap to release after the part is done sintering. So once it's cooled down and comes out of the oven, you can gently tap it with a hammer and it pops the supports right out. And so that's how supports work. But if you're thinking about optimizing them, support material is material that's going to take up more time in the printing process. So if you're trying to print your parts faster, it generally helps to minimize your supports. So to optimize them, there's a couple things you can do to eliminate certain supports in areas where you don't actually need them. So for horizontal holes or horizontal bores, One of the things, and really it's actually not even so much holes, it's any geometry that's a horizontal sort of path. You can take a circular cross section and add something like a teardrop or change it to a diamond shaped profile to entirely eliminate support generation in those channels. And so, as long as those overhangs are at 45 degrees or less from the vertical, it won't generate any support material in that channel. And the same thing goes for just overhangs and like sort of external overhangs in general. A lot of times, with machining, for example, if you're designing a part for it to be machined, a horizontal overhang is pretty easy to machine. But with 3D printing, it's going to have to add supports there. So if it doesn't need to be just a straight cantilever or like a 90-degree cantilever, if you can chamfer those sections, you're going to be able to also minimize the amount of support, and that'll print faster, it'll wash faster, and it'll generally produce a better part throughout the process. Also on the sort of topic of sort of optimizing your parts for printing, you also want to think about print orientation. Even when you're designing for the part, to think about the print orientation. And so you really want to maximize your contact surface with the print bed. All parts are still going to be printed on a raft, but you still want to ensure that the best parts maximize that sort of level of surface area, level of contact area with the print bed. The other thing that'll allow you, or helps to do, is to ensure that your holes and your sort of critical tolerance cylindrical features have a cross section that's in the XY plane. In general, because you're building up a part layer by layer, and because you have to have those parts be sort of supported, you're not going to get as circular holes if they're horizontal versus if they're sort of their main axis is normal to the print bed, kind of their main axis is in the Z direction. So, if possible, and we're thinking about, hey, if you have functional requirements that certain holes need, or certain features need critical tolerances, ideally those cross sections are going to be in the XY plane. And then I had we did have a question about, can you design your own support features into your parts? And then you absolutely can. Generally what you'll want to do is design a separate body that exists. And it's definitely more of an advanced design technique, but in cases where you need a specific support, or you need something more specific than Eiger can offer you, you can design your own sort of separate body as a support body in your favorite CAD package, and import both, or basically export both those bodies as a single STL when you import it into Eiger. Definitely will require you to have a little bit of design or tailor your design to the process, and you will need to leave gaps between your CAD supports and the part itself, so that you can allow Eiger to add in ceramic and support material between your supports and the part. But it's certainly possible, and it is definitely more of an advanced technique to kind of get what you need. Okay, so let's say we've designed for our part to print well. We've modified our design to print well. Now we got to think about washing times and how we can sort of optimize that. So the washing process is going to wash a part from the outside in. It's basically going to wash away the wax in the outer surface layer, and then when that wax is gone, the washing fluid can dissolve further into the part through those sort of spaces that were created from the wax being washed away. So it's always from the outside in. And so for a part like this, this is a sort of metal gripper jaw for a robotic automation application. And so for each of these, with the way I've currently set it up to slice, it's going to take about 9 hours to print these, but it'll take us about a day and a half to actually wash each of these. Now, the washing process is a batch process, so once I print 3 of these, I can wash all of them at the same time, and all 3 of them will wash in a day and a half. But that's still an extended amount of washing, so if I wanted to do this more quickly, I can design in features to actually wash faster. So let's take a look at what this part will look like in CAD. And so this is the part in CAD, and if I were to, simply in its current design wash this part, we might see something like this. after 24 hours of washing. And so the green is basically is representing the part being fully washed. So you can kind of see that sort of in the middle of that part, it might not have been fully washed after 24 hours. So this is why, it takes a day and a half roughly to wash this part. And the reason is because the wash fluid can't penetrate, there's no channels for it allowed to penetrate to the center of that part quickly. So it has to wash from the outside skin in. So what we can do to optimize for wash times is add holes or add channels to allow that fluid to circulate and sort of touch internal sections of those features much faster. And so you will have to balance whether this is functionally appropriate for your part. Obviously, if I'm now adding, a little bit of, or I'm taking away material from my part, so it would need to be, we want to make sure it's strong enough. But in cases where that that's going to be the case, you can add channels like this to really allow the wash fluid to get into the part, sort of much more integral. Excuse me. You can make the wash process much more integral to the center of the part, and you can speed up that wash process. And you can see basically this part has been fully washed after 24 hours. So once the part is washed, we then want to think about designing for sintering. And so sintering is a little bit interesting because, when you're designing for printing, overhangs are more of a, can I lay down material on this overhang without it, does it have a, does it have material underneath it to print on top of? With sintering, it's less about the angle of the overhang and more about thinking about how much weight and material and mass of material is sort of above an overhang. So what you'll want to think about is you want to sort of build in or redesign your parts to make sure that they are supporting things like top-heavy cantilevers. So for one, if you could print this part on its side, that might change things significantly. But if this part, if this cantilever that on the left that we're showing, if that was particularly long, had a high aspect ratio, maybe that sort of thicker section at the top of that cantilever, or that sort of lofted surface was heavier, you might think that and let's say it was designed so that support material wasn't generated here. It still might be a little top heavy, and you got to imagine that the part is being brought up to about 85% of its melt temperature. So while it still does have some hot strength, it is going to be a little bit more or a little weaker than it would be obviously when it's a solidified metal part. So you will want to think about adding some sort of support or like a rib or a gusset like you see here to support a structure like that. And we are getting a question about, do parts need to be printed, washed, and sintered all in the same orientation? And they need to basically be printed and sintered in the same orientation. They don't actually need to be washed in the same orientation. And the best example of that actually is if you printed something that looked like a cup, where it could hold liquid. One of the things you'll actually want to do is probably wash that upside down. And that's going to ensure that you're not sort of concentrating the heavier wax in the bottom of that cup. You want to make sure that that wax is able to be washed out. And so something like a cup feature, for instance, will probably wash better if you were to sort of place it with the cup side down, but you may have printed in a different orientation. And as long as you print and sinter in the same orientation, you should be good. But there may be some cases where you'll actually want to wash in a slightly different orientation. So that was a good question. So after thinking about some of these top-heavy cantilevers, the other thing you might want to think about is to place fillets on extremely sharp edges. So one of the nice things about the atom process versus maybe some other, maybe laser-based or sort of direct energy powder-based processes is that the sintering process occurs over a much longer period of time and in a much more gentle fashion. So you're not really seeing a really, discrete or sharp sort of sintering process layer by layer. You're sintering the part as a whole body. And this is really nice because it generates a lot less internal stress. But at the same time, you still are, your part is still shrinking down, albeit gently and over a much longer period of time, but it is going to shrink down a little bit. So one of the best things you can do is to avoid stress concentrators like sharp edges. And so, there is a possibility with extremely sharp edges in a part that you may see some deformation during the sintering process. So one way to avoid this is to add, gentle fillets. And in this case, we're showing you here, we've added some pretty large fillets where the smaller section of this part kind of meets the larger section. That probably isn't really that necessary. But adding sort of gentle fillets to a lot of these parts will produce better sintering behavior. And the nice thing is you can produce a lot of parts that might be difficult, if not impossible, to machine otherwise. So especially sort of rounded over fillets on external surfaces, not something that's really easy to machine. You usually would probably just break the edge with a chamfer, but you can certainly print it. The printer is much better at replicating geometry like that. Oh, and sorry, we did get one other question on why the printing and sintering process needs to be done the same orientation. The main reason for that is that in general, sort of the gravity or the while you're printing, you want to print on top of foundation because gravity is sort of pulling down the metal down to the layer below it. There's also a degree of extrusion there, but you do want to obviously print onto a bed of supports. In the same way, when you are sintering, the hot strength of the part is a little bit weaker, so you want something to be supporting those same surfaces. So there's a few different phenomena going on. There's a little bit different physics during the printing versus sintering, but there is still a somewhat related sort of physics that you have a hot, slightly weaker part while it's being printed or while it's being sintered. So you want to support that. Okay, so all right. So finally, let's just now you've made sure that your part makes sense economically to print. You've chosen a geometry that's good. Maybe you've modified it a little bit to take advantage of the printing process more. So the one, and this is really doesn't occur after you've printed. It's really something that happens during the design phase as well. But you do want to also plan for what kind of finishing operations you're going to take. And so what that means is that we generally suggest that you post-process your parts in either the green or the sintered state. And so what that means is we really want to either post-process something right after printing and before we've washed it, and actually in general, what we more strongly suggest is that parts are post-processed after they've been fully sintered. So what that looks like, this is a pretty typical surface finish after printing, after wash, and after sintering with no finishing done to it. So this is pretty much the raw surface finish you'll see. And in general, it's pretty good. I mean, you should assume it's effectively on par probably with maybe like investment casting or a nicer sand casting, maybe a smaller grain sand casting. It's definitely better in general than, let's say, like a cast iron pan, for instance. But it's probably gonna be on par with maybe a finer sort of investment cast, maybe. When you wet sand it, which is basically in the green state, so basically what you do here is right after printing, you'll take that green part and you'll put it under water and use some wet, dry sandpaper and sort of clean up that surface gently. So the advantage here is that because it's in that green state, it's effectively composed of plastic, wax, and metal powder. And it's going to finish much more like a crayon or a bar of soap. And it's very easy to finish, even when you're talking about really hard metals like tool steels. It's not fully sintered at that point, so or it's not sintered at all in that point. So you're not running into the hardness limitations that you'll run into when that metal is then fully sintered. So it can definitely clean up that surface finish, and you can kind of see here if I go back real quick, you can see that it's definitely has a smoother surface finish. Although you obviously notice that it's clearly been hand sanded, so it's not a perfect finish by any means. And you also notice that it kind of wore down the embossed or exposed two here to identify that face. Okay, so another option you can do is to actually, and I believe this may have been green sanded and then belt sanded and polished after sintering as well. But you can certainly do any sort of, normal belt sanding, grinding, and polishing post-sintering. The nice thing about this is it's going to produce a much smoother, much finer surface finish, but it will take a little bit more effort because obviously at this point, this part has been sintered, and so it's at its as sintered hardness. And actually, on that point, we did get a couple questions about that as far as, what are the metal characteristics post-sinter? So they're generally what we consider an as sintered state. Oftentimes, for instance, with 17.4, it's pretty close to a solution annealed state. It's certainly not hardened out of the sintering oven. You can pretty much perform any sort of heat treating and post sinter, hardening, heat treating, what have you, on any of these metals, as long as you can do it on the underlying metal. So for 17.4, you can precipitation harden it beyond what you get out of the furnace. And to Marco's point earlier, at the intro of this talk, you can find a bunch of data sheets online on our website at markforged.com that'll kind of go into more about some of the hardness or potential hardenable or potential hardnesses that these metals can achieve. I believe 17.4 comes out of the furnace with something like a 30 to 35 Rockwell C hardness, and then can be, I believe, hardened up to maybe like 40. But don't quote me on that. You'll have to take a look at the data sheet. And then we have some tool steels coming out. Probably the first one will probably come out as H13 down the road a little bit, and that I believe can get up to about 45 or 50 Rockwell, I believe, maybe a little bit higher than that. So the nice thing is that when they come out of the furnace, they will be in that as sintered state. So they'll be a little bit softer and a little bit easier to work with, but it's still going to be a lot more effort to sand and polish, for instance, a part like that than it would be in the green state. So that's sort of one of the trade-offs there. Finally, you can also machine these parts. There's no problem in machining them, and this is actually what it looks like when you did that post-sintered machining. I believe we obviously didn't use a face grinder or a face mill on this, so it could have gotten a even higher surface finish, but you can certainly machine these parts. In fact, we expect that most customers with precision applications will want to do that. You should sort of treat these parts, as I mentioned before, kind of like a precision casting, and so that they're definitely have better tolerances in most cases than a sand casting part, or a sand casted part, but you still will need to machine critical surfaces. If you have a bearing press fit or anything like that, you'll want to clean that up with a machined surface. And so just to give you an idea of some of the finishing trade-offs here, really, and why we suggest post-sinter processing, whether it's machining, grinding, tumbling, polishing, et cetera, is that the green state processing is much faster material removal and is significantly less effort to remove material. The parts are a little bit fragile in the green state. Like I said, they're kind of the consistency of soap or a crayon, so certainly can be broken if dropped in that state. And it's also it's much tougher if you're hand sanding something to hit your critical sort of tolerance limits, and also there's limits to what you can produce in the surface as a surface finish. It's not going to get the same shiny surface as you would with a machining or a grinding step. But it is something that in certain cases, especially if you have a surface that needs to be smooth but doesn't really need to be precise, it might be a good way to get your finishing sort of started and kicked off. In general, though, we're definitely suggest for any critical and high precision work, you definitely want to process it after the sintering state. And we've done a bunch of work with especially machining and belt sanding as well. And so just to give you an idea on the how to plan for stock removal and what you should be considering adding, you'll want to effectively make sure you're not breaking through the walls of these parts. So actually it kind of goes back to a question that I think we had, which was sort of, what do you do if you want a hollow part, or how do you remove material from the inside? So by default, you should design your parts as solid parts in CAD, and much like a lot of typical 3D printing or 3D prints, especially for extrusion-based technologies, we actually will automatically generate a triangular honeycomb infill in that part to help lightweight it and to speed up the printing process. So basically with when you're planning for sort of a machining operation, you just want to make sure that and in general, you don't have to take off very much material, but you definitely want to, really just more think about like it from a skim pass standpoint. So, something from, 8 to 20 thou or, 200 to 500 micron. In the XY, and then in Z, even less, maybe like a half thou to, 5 thou to maybe like 10, 12 thou, or just 100 to 300 microns in Z. You generally don't need to remove much stock, and that'll make sure that you're squarely within the sort of shell layers of these parts, and get a really nice surface finish without actually breaking through or compromising the strength of the part. Okay. So that sort of ends the planned sort of content I had. And I definitely want to give you guys plenty of time to ask questions and kind of get some Q&A going. So.
Mm-hmm. So we're going to switch to Q&A in just a minute here, just to do a little bit of housekeeping. Before we do, I saw a few questions come in about the recording of today's webinar. We are recording today's webinar, and we will be posting it on the website. And if you registered or if you attended, you will receive a link to that recording. It usually takes us about a day to process that and put it on the website. So expect that link to come in sometime around the same time tomorrow. We also did get quite a few questions about specifications. So whether that's print bed sizes, material hardnesses, strengths, tolerances. Nick is going to speak to some of those as best he can today, but if we do encourage you to go to our website at markforged.com, because we have material data sheets there and printer data sheets there that can go into more detail than we have time for today.
Okay, cool. So I'm going to go through some of the Q&A we got going, and let me see if I can just dismiss some of the ones we already answered. So we got a question early on about tolerances, and I may have answered this, but I just want to make sure we kind of go back to that. So in general, you should assume these are near net shaped parts that are pretty similar to maybe a precision investment castment, but they're generally about plus or minus 5 thou per inch, or if you're designing a metric, that's about basically plus or minus 125 micron per 25 millimeters. So definitely pretty precise, but they will need a little bit of post-process cleanup. Let's see. So we got a question on maximum part size. So there's kind of two answers about maximum part size. So the machine itself can produce a part that's, I believe, up to about, I think, 250 millimeters by 220 by 200 millimeters. You have to scale that down by about 17% to account for sort of the expansion of the part due to scaling up. So it's basically, 17% less than those numbers. However, you also want to think about and this kind of goes back to the economic considerations. You also want to think about, does that part make sense to print? What we found is that generally the best use cases, and by far isn't all of them, the best use cases tend to be things that are parts that are bigger than roughly your thumb, and then maybe like as big as up to about your fist size, your hand size, maybe like a softball size. You certainly can print bigger parts, and you certainly can wash and sinter them, but the time involved in printing something much larger than that, or washing something much larger than that, sometimes sort of negates some of the benefits gained by 3D printing. I mean, one of the things that 3D printing can really offer you is much faster lead times generally than machined parts, and so you get the most benefits through parts that are maybe roughly in the thumb to fist size sort of range. So just kind of give yourself a range there of what also works economically. Okay, let's see what else we got here. So we got a couple questions about what's the capabilities of Eiger are to sort of adjust various layer heights or infill percentages or things like that. So those are all options that are sort of on our planned future roadmap. Right now, we print with, I believe, 4 walls thick, and I think 4 layers or 4 roof and floor layers, which basically means that the metal shell surrounding your part is going to be about, I think, after shrinkage, something like roughly in the 1.2 to 1.3 millimeters wide as a shell, and I believe is something like 600 microns or about 600 microns thick on the top, roof and floors of the parts. And that's also going to then have a 37% triangular infill internally to the part, so making it nice and strong and lightweight, almost like a single material sandwich panel. And we're going to be printing right now in a roughly, believe 200 micron layer height that's going to shrink down to about 160 or so micron. And so those are the settings that we know work great every time. And with the Metal X, we're really trying to make sure that every part that you put through it and every part that comes out gets a really nice, high quality part. And so we're continually optimizing this in-house. And so as we sort of get the software or get the sintering behavior to a point where we feel that it's going to be just as repeatable as you put a part into Eiger, print it, and get the part you want, we'll open up some more of those settings. What we really want to make sure is that every part that you print is exactly the part that you want. And so that's why we're really trying to focus on not really releasing sort of beta features, but really just making sure that every part has great quality. So just to summarize that, we will be releasing more functionality and ability to customize your parts down the road, and it's definitely on our roadmap. So sort of look forward for those, or look to those updates down the road. Let's see. So yes, someone asked the question, does Eiger give us an estimate for the wash time? It will absolutely give you a sort of upper limit on how long you need to wash the part. You can underwash a part, but you cannot overwash a part. So when in doubt, the best thing to do is just leave it in the wash for a little bit longer. I've sort of put parts in the wash and forgotten about them over Labor Day and came back a week later, and it was certainly not a problem. All the wash is doing is dissolving out the wax. They really can't overwash a part. Someone asked us that our atom process seems to be very similar to MIM, except for the production of the green part, correct? And that's definitely true with a couple differences. So for one, with MIM, you have to basically cut a traditional injection mold tool, which can be time consuming, very expensive, et cetera. And so we definitely don't have to do that. Instead of cutting a tool and injection molding into that tool, we just print the part directly. Another nice thing about this is we actually, because of that, or because of the atom process and because we're 3D printing it, we can also produce parts that are much larger than MIM. Generally, if you ask anyone who's a MIM expert or a MIM house, they'll suggest that you MIM parts that have less than 100 gram shot size as a starting point. There's certainly exceptions to that, but generally you'll want to have relatively smaller parts, and they can only shoot about 100 grams of material at a time. With the atom process, we can do much larger parts, significantly larger parts than you'll see for MIM. And we don't have any of the tooling limitations that we do with traditional, or you do with traditional MIM. Let's see what else we have here. So someone asked about hollowed out volumes, and do they need to have openings implemented like you would with a powder bed based or DMLS style 3D printer? We don't need to have, we do not need to have sort of holes into the internal structure of a part if it's been infilled or with the sort of algorithmically generated infill that we have in Eiger. The reason is that there's no material that we need to release out with a powder bed type process. If you want to have a hollow infill, you got to sort of leave some holes for that powder to escape the part before you kind of continue on with the finishing it. Because we're printing this as closed cell infill, we don't have to actually worry about any of those kind of things. So we just basically take a solid part and it'll automatically hollow it out and infill it. make it really light, but also really strong because the exterior shell is where most of the loading and the forces are. And that's where we have, the solid metal shell. So we got a couple questions about, can we sinter different parts together? And that's absolutely the case. As long as you have space on the ceramic setter plate that sort of all of your parts have to live on in our Sinter 1. As long as you have space for that to put those parts without them touching each other, you can put as many different parts with as many different geometries as you like. They basically just have to be made of the same material. So, when we quite soon release some of our tool steels, you won't be able to sinter a tool steel and stainless, for instance, on the same setter plate or in the same sinter run, but otherwise different geometries are no problem. We also had a question about, can you thread into such parts or to thread into metal printed parts? And the answer is definitely yes. And it's sort of a question of what size thread you're doing. So for thread sizes larger than, I believe, like roughly like an M10, I think. And it's something like about a half inch, roughly about a half inch thread if you're using Imperial. You're going to want to design in the thread into your part. And that's because basically the difference between the major and the minor diameter of threads above those sizes are large enough that they could, if you tap just a hole printed at the tap drill size, you might actually see the tap break through the shell or the walls of the parts. So in that case, you want to actually print those threads, and then they generally print pretty well, and you may not need to even chase them. But if you want a slightly more precise thread, I would chase that thread with a tap afterwards. For holes smaller, or threads smaller than an M10 or about a half inch, you generally can just design in a hole to the tap drill size and then just tap that part afterwards. You really can probably print down to about an M3 thread if you really wanted to, but in general, your best bet for those smaller size threads is just to print your tap drill hole size and then thread it after the fact. Let's see, what have we not talked about? So someone asked, is it possible to reach a surface quality after printing for plating operations? And it's absolutely the case. You can, in fact, actually, especially with injection mold inserts, or we suspect with people that are looking to 3D print injection mold inserts, we may want to sort of do some sort of hard coat or hard plate afterwards. I don't know if that's necessarily a nickel or something more sort of advanced, but you absolutely can reach a surface quality for plating. And in fact, we expect that in some cases, that's probably how certain applications will produce the best end part. Same kind of a similar question we got, can I secondary CNC or EDM these parts? And absolutely, we showed you the post-sintered CNC machined part. EDM is the same. In fact, I have a couple parts right now that I worked on with some customers that they're going to clean up the surface finish with an EDM or wire EDM just to get a much tighter surface finish. That should be pretty interesting, but there's no reason why it wouldn't work there. Someone asked, did I say H13 tool steel? And I did. It's not out yet, but it's probably the first tool steel we'll release sometime, probably either end of this year or early next year. Let's see, is there any? Okay, so someone asked, is there any anisotropic feature of mechanical properties or density pores due to printing orientation post-sintering? So a couple good questions in here. So from a mechanical standpoint or a material property standpoint, the parts are very, or they're not perfectly, but they're pretty close to isotropic, or there's a much stronger isotropic level of strength mechanically or materials wise than there is with typical sort of 3D printed plastics. And that's due to the fact that you're not really making your part based on sort of layer by layer printing. The metal structure of your part, or the grain structure, is developed during the sintering process when you're sintering that whole part as a whole. So the grains or grains can basically grow across layers, and so you're getting a much stronger overall part than you'd see with like a traditional plastic printer. On the aspect of bulk anisotropy, though, of your part, you obviously are printing with an infill that's a triangular cross section. So there's going to be a little bit difference, depending on loading direction, of the part. There's going to be a little bit of a strength difference due to that infill percentage. So there will be a little bit, but it's much more consistent than if you're familiar with plastic 3D printing, it's going to be much more consistent and much stronger than that. Let's see. Someone asked what the density of a sintered part is compared with a cast part. So there's kind of two components to that answer. There's where you've actually laid down metal paths during the printing process. So after sintering, we're getting greater than 96% density where we've actually laid down material. And that's obviously the case because we have an infill. So we're also printing at about 37% infill. Generally cast parts, to my understanding, have or can contain quite a few voids. So you're not going to really see the same level of porosity that you would with a cast part in our printed parts, and at least in terms of if you're looking at specifically where we've laid down metal. Obviously, we'll have that infill, so that's going to sort of add a like larger void fraction, but at the microscopic level, there's going to be a lot less void fraction than with a cast part. And I think that's most of the ones that we I think we've answered a lot of these.
All right. As we slowly bring things to a close today, I'd like to just pitch once again the wonderful work that our web team has been doing at markforged.com. Aside from just the data sheets that I've mentioned a few times earlier, that Nick has mentioned, we've also been building out a new applications section as well as a new learn section where you can read in-depth articles and get more information. So if you haven't been to the website, even in the last few weeks, we'd encourage you to revisit it. And that is, of course, also the place where if we did not get to your question today, you can reach out to a Markforged representative and set up a individual webinar, something like a 10 or 20 minute individual consultation where they can help you run through your specific applications and talk about how Markforged technology can help you there. Thank you so much for joining us today. You've been a great audience, and we hope you have a great rest of your day and look forward to seeing you at the next webinar.